Okay, here, let's use what we've learned to figure out an example. Let's find the probability of finding a particle in the first 10% of an infinite well. Here, 1 second. Okay, so our goal is to find the probability that a measurement would find a particle in the range 0 to L over 10. Okay? Okay? Like so. And of course, it's straightforward to analyze this. All we have to do is imagine the probability density which I've tried to sketch here. Let's say for the n equals 2 state. And then we just need to figure out the area under the curve in the region of interest between x equals 0 and x equals L over 10. Now, before we do the problem, let's just do something for comparison. If this were a classical particle, then we know that the probability density is uniform. And so the probability to find the particle between 0 and L over 10 would just be 1/10, because the particle is equally likely to be found anywhere in the box, according to classical mechanics. However, for quantum mechanics, the probability is different. Here, we have to get the probability by integrating the probability density over the range x equals 0 to x equals 10. And the probability density is just absolute value of the wave function squared. And so this is the absolute value squared of our wave function, which we've just found can be written as square root of 2 over L times sine of n pi x over L. Okay? So finally, our goal is to do this integral. It's the integral from x equals 0 to x equals L over 10 of our wave function here. Oh, let me write this slightly differently. Of the wave function squared. We have a constant factor root 2 over L. When we square that, it becomes just 2 divided by L. And then we have sine squared n pi x over L dx. And there we are. That's the problem we have to solve to find the probability density. Okay? I'll go through this quickly because it's just like the problem we just did when we normalized the wave function. So we can solve this again by doing a substitution by calling the argument of the sine function theta and then going forward. So what we'll get in this case will be 2 over L. We'll have a factor of L over n pi times our integral, which now looks like integral 0 to n pi over 10 of sine squared theta d theta. And the result of this, just using what we found before, is the following. Also canceling these factors of L, we have 2 over n pi.
I found this on the web.
Excuse me, 1 second. Okay. Continuing then, we got rid of Siri finally. We have 0 times theta minus 1/2 sine of 2 theta from evaluated at n pi over 10 and 0. And this becomes 1 over n pi over 10 from the first term minus 1/2 sine of n pi over 5. Okay? And now just simplifying this, we get 1 over 10 minus 1 over 2n pi times sine of n pi over 5. And that's our result. Okay? Wow. Finally, let's just evaluate this and see what it looks like. Notice we have a general expression here that will work for any value of n. So let's evaluate it. Okay? Here, I just want to copy something over so you can look at it while we're doing this. 1 sec. Okay, now we can make a table. Oops. Of this probability for different values of n. For the case when n is equal to 1, then a moment with a calculator will show you that this evaluates to 0.0064. For n equals 2, we get 0.0243. For n equals, skipping a few values here, for n equals 12, we get 0.1078. And now you don't need to find a calculator to find this. What's the value for n equals infinity? Here, look at our result. Notice that there's a factor in the n in the denominator of the second term. If n goes to infinity, then that term will go to 0. On the other hand, the sine term will always be between +1 and -1. So as n goes to infinity, the second term in the equation will definitely go to 0. And if the second term in the equation goes to 0, we'll just be left with the first term, 1 over 10. Okay? Now I want you to contrast that with the result from classical mechanics. For classical mechanics, the probability was just 1/10 because it was uniform, and so this is easy to find that result. And the point I wanted to make is, look, the classical prediction is equal to the prediction for the quantum case in the limit that L goes to infinity. This is an example of what's called the correspondence principle. Because quantum mechanics has to explain everything in the world, predictions from quantum mechanics should agree with classical predictions in the limit that the quantum numbers become very, very large, since that's the limit that describes classical mechanics. All right, let's stop here, okay?